We shall look next at the differences between two-phase and three-phase separators, before discussing the design considerations of separators in general.
When oil and water are mixed with some intensity and then allowed to settle, a layer of relatively clean water will appear at the bottom. The growth of this water layer with time will follow a curve as shown here. After a period of time ranging anywhere from 3 minutes to 20 minutes, the change in the water height will be negligible. The water fraction obtained from gravity settling is called free water. It is common practice to separate the free water before beginning to individually treat the remaining oil and emulsion layers.
Three-phase separators, sometimes called free water knockouts, are used to separate and remove any free water phase that may be present. Because the flow stream enters a three-phase separator either directly from a producing well or from another separator operating at a higher pressure, the vessel must also be designed to separate any gas which flashes from the liquid, as well as the oil and water. Hence the name three-phase. The basic design aspects of three-phase separators are identical to those discussed earlier for two-phase separators. Three-phase separators are designed as either horizontal or vertical pressure vessels. The only differences are that more space must be provided for oil-water settling, and that some means of removing the free water must be added.
Here we see a cutaway version of a horizontal three-phase separator. The fluid initially enters the separator through this inlet and immediately strikes an inlet diverter. This particular inlet diverter is made of some pieces of angle iron which abruptly change the direction of flow of the fluid that's entering the separator. This does the initial gross separation of liquid from gas. This liquid settling portion of the separator here needs to be sized to allow enough time for the oil to begin to form a pad on top of the water layer at the bottom of the separator. The gas, of course, comes to the top of the separator. In this particular vessel, we also have some grating here which acts as straightening vanes to smooth out the flow of gas and liquid through the separator. Next, we find a wave breaker that prevents any surges of liquid from forming waves that flow horizontally through the separator that might re-entrain gas into the liquid phase at the bottom. In this particular separator, we next see a wire mesh mist extractor. The wire mesh mist extractor coalesces any tiny droplets of liquid that may still be entrained in the gas that's flowing horizontally at the top of the separator, and coalescing these liquid droplets allows them to fall down to the bottom and re-enter the liquid phase at the bottom of the separator. Here we have another wave breaker, and finally we get to the end of the separator that's responsible for the separate dumping of the oil and water phases after they've been separated. We see here this weir which allows the oil on the top of the water to spill over into this bucket here, which is monitored by a float or a level displacer inside this bucket, which operates this controller, which operates this liquid dump valve down here for the oil phase. Just behind the oil bucket, we see another float which senses the interface between the oil and water within the separator. This float operates another pressure-controlled dump valve down here, which dumps the water from the bottom of the vessel when the interface gets to the certain height that needs to be. On top of our separator, we also see a gas outlet where the gas is taken off, and just behind that, another gas outlet with a safety valve to the flare line in case the pressure in the separator gets too high.
Here we see a typical configuration for a vertical three-phase separator. The flow stream enters the vessel through the side, as in the horizontal separator, and once again the inlet diverter separates the bulk of the gas. A downcomer is required to transmit the liquid through the oil-gas interface, so as not to disturb the oil skinning action taking place. A chimney is needed to equalize the gas pressure between the lower liquid collection section and the upper gravity settling section. The spreader or downcomer outlet is located beneath the oil-water interface. As the oil rises from this point, any free water trapped within the oil phase separates out. The water droplets flow downward, and any oil droplets trapped in the water phase tend to rise countercurrent to the water flow.
3 different methods of control are often used on vertical three-phase separators. The first is strictly level control. A regular displacer float is used to control the gas-oil interface and regulate a control valve dumping oil from the oil section. An interface float is used to control the oil-water interface and regulate the water outlet control valve.
The second method shown uses a weir to maintain the gas-oil interface level in a constant position. This method results in a better separation of water from the oil, as all the oil must rise to the height of the oil weir before exiting the vessel.
The third method uses 2 weirs, which eliminate the need for an interface float. The interface level is controlled by the height of the external water weir relative to the oil weir or outlet height. This is similar to the bucket and weir design for horizontal separators.